Okay, so welcome to Math 310, Introduction to Modern Algebra. This is lecture 20. So we're going to continue discussing orbits. We'll discuss stabilize again, and then we'll get to some of the CeeLo theorems. And these are absolutely wonderful in terms of getting a sense of what possible group structures can there be for a given size. So frequently in life, you might actually have some information about a group, and you want to figure out what does that tell you must be true? What does that tell you might be true? How uniquely can we classify? And we rolled up our sleeves and we did some calculations in the beginning, and we saw just how bad it can get as the size of the group grows. When the size is pretty small, it's not so bad. There's not too many possibilities. But once we got to something, I think we were looking at something of size 9. There were a lot of possibilities. What could x times y equal when x and y were two elements of order 3? So you're supposed to think, very briefly about the following. This is an extremely famous problem. Has anybody seen this one before? Okay, so if you've seen this before and you remember the answer, don't say the answer. All right, you can say the naive answer. So the way it works is you have 100 prisoners, and we will assume that they are mathematicians who try to divide by 0. So they've been sent to jail, but they are extremely intelligent. They have wonderful logical skills. And in this problem, the 100 numbered prisoners must find their number in the draws to survive. So there's 100 draws. Each draw has one and only one number. So maybe number 1 is in 15, maybe number 2 is in 23, et cetera, et cetera, et cetera. No draw has 2 numbers. Okay, everybody clear? And the rules state that each prisoner may only open 50 draws. They cannot communicate with each other. They can't leave a draw slightly open to indicate to the next prisoner what was in that draw. If I open a draw and I saw a 1, I leave it open 1/1000th of an inch. If it was a 2, I leave it open 2/1000ths of an inch. You can't do something like that. Okay? And so they can only open 50 draws. They can't communicate with each other. If all 100 prisoners manage to find their own numbers, they all survive. If even one prisoner fails, they all die. Okay? At first glance, this should look hopeless, or almost hopeless, essentially hopeless. What is the probability a given prisoner, if they just guess randomly, will find their number?
50 out of 100.
50 out of 100, which simplifies to 1/2. So the naive estimate, probability that they all live, is going to be 1/2, and to what power? 100. Right? Each prisoner has a 50-50 chance because they get to look at 50 out of 100. So it might be better, as was suggested, to write this as 50 over 100 and not 1 out of 2. So this is going to be 1/2 to the 10th to the 10th. Yes? I'm doing this because I can calculate this number very quickly in my head. 1/2 to the 10th to the 10th. What's 2 to the 10th approximately? 1,000, right? We did that in the Benford's law. So this is approximately 1/10 cubed to the 10th, or about 1/10 to the 30. So whenever you see a number, you want to try to put it in perspective, especially those of you who are going to become teachers. How do you get a class to understand a number of size 10 to the 30? Can you give me something in everyday life that might be like a 1 in 10 to the 30? What did I just choose?
Speck of dust.
Speck of dust. Anybody remember Avogadro's number? A mole is about 10 to the 23rd, right? 10 to the 7 moles in here? Yeah, order of magnitude, maybe 10 to the 7. This is on the order of, I choose a speck of air, and you choose a speck of air, and we chose the same one in this row. That's the order, because whatever one I choose, you've got like a 1 in 10 to the 30th, maybe chance of matching what I have. That should give you some sense of just how improbable a 1/10 to the 30 is. Okay, so when you first look at this, the way they often portray this is the warden is having fun with the prisoners. And he's giving them a chance, but not really. Right. The people who've seen this before, do you remember the solution? Or what do?
You start it with a locker associated with your number. Find the number in there, then go to that locker.
Good. So
Or
you
that, yeah.
so you open one. If one has a 7, then open 7. If 7 has a 23, open 23, ... So maybe it's 1 to 7 to 23 to maybe 81 to 4 to 97, ... Will it eventually loop back to 1?
Yes.
Why? So must it loop back to 1? Why?
There's only like one number in each thing, and
Right.
there is a one, so.
There is a
eventually you'll
1.
Find one that will take you back to the one.
And you can't go back to something you've already seen. You have to go to something new. So eventually you will hit 1. So yes. So we know this will work. The danger is it might take too long to work. What's the only way that we have trouble? Well, if it takes more than 50 steps to loop back. So, okay, if less than or equal to 50 steps. What we're really doing is we have a permutation. Here we have the numbers 1 to 100. And maybe it's, n1, n2, n3, ... n100. And we can break this up into a bunch of disjoint cycles. And so maybe the first cycle is, m1 through mk1 over n1 through nk1. And then the next cycle is maybe mk1 plus 1, ... mk2 and k1 plus 1, ... nk2, ... We have a bunch of disjoint cycles. And we need each to have length less than or equal to 50. So if each cycle has length at most 50, then everybody will get there. So the only danger is if we have one really long cycle. Is it possible to have a really long cycle? What do you think? Okay, how could you have a really long cycle?
Each locker has a number that points to the next one.
Yeah.
And
Really, really easy, right? 1, 2, 3, ... And I guess it would be 99, 100, 2, 3, 4, ... 101. I could easily do something like this and give you a very long cycle. So if the warden wanted to be evil, knowing the strategy you're using, not a problem. Yes.
But couldn't you see the pattern? Like, since they're perfect conditions.
1, 2, 3, ... 49, 50, 51, 52, ... 98, 99, 100. So I could do 2, 3, 4, ... 50, maybe 52, 51. I could maybe throw a few things off. Let's see, I haven't done 49. 49. 98, 100. I could maybe play a couple of games like this. Oh, and I haven't used one. Maybe I should be using one somewhere. Maybe I'll put the one over here. So if they're trying to use the pattern, I could tweak it just a little bit. And again, I could make it so it works maybe for 1, 2, and 3, but maybe when I get to 4, 5, and 6, it doesn't work. So you could start to believe, and you might then jump ahead, but it's just guessing. And at this point, as soon as you're guessing, you're no longer certain. So the question becomes, if I give you a random permutation, what are the odds that all of its cycles are at most 50? So how many of you have ever done math competitions? Okay. One of the first things you should do in a math competition is you should learn fun facts about the year. Is the year a prime number? What's the next prime after that? Does it have an interesting factorization? Sometimes these things come into play. One of the other things whenever you do competitions is you look at the numbers. So what numbers did I give you in this problem? 100,
50.
50. In general, how do you think those numbers what do you think they generalize to? And so a cycle of length 51 was bad. How do you think these generalize? So 100 becomes n. What do you think 50 becomes? N over 2, and maybe n over 2 plus 1. The key fact is that I'm giving you 50. The problem would be much harder if I said you could only open 40 boxes or 30 boxes. 50 is actually very nice. So we only lose if we have a cycle of length 51, right? Could you have 2 cycles of length 51 or more? Why not?
Because then you need to have more than 100.
You have to have more than 100. So can have at most 1 cycle of length greater than or equal to 51. And that's why 50 was so crucial here. If I wanted to do this where you could open 49 boxes maximum or 40 boxes maximum, the problem would be a lot worse because then you could have 2 different cycles. If I gave you at most 30, then it's even worse. You could have 3 cycles of length 31. So a lot of times when you're given a problem, stop, pause, look, and ask, are there any reasons behind why they chose these numbers? Usually, yes. Sometimes they choose numbers to mislead you. But frequently, especially at the lower levels, the numbers are chosen for a reason, and it's crucial here. So there's a standard analysis for this. I just pasted this from Wikipedia, and it goes through and it calculates what's the probability that you have a cycle of length L greater than 50. And so we have to choose L numbers from 100. So there's 100 choose L ways to do that. Okay, and now we have an L minus 1 factorial. So how many ways can we make a cycle with L objects? Well, I might as well start without loss of generality for convenience. Let's say our numbers are 1 through L. I'm not putting the numbers on a line. I'm putting the numbers on a circular table on a clock. So without loss of generality, you might as well just rotate it so the number 1 is at the top in your cycle. It's got to be somewhere. So you really only have L minus 1 things to place. It's having people sit at a table where you can spin it and then just have one distinguished person at the key spot versus having people on a line and then it matters who's at the end. Because there is no edge. It goes round and round and round. It cycles through. That's why, so this is the number of ways to choose L numbers. This is going to be number of orders on a cycle or a circle. And then what's the 100 minus L factorial? That's how many ways to order what's left. Order what is left. And so when you go through and you do the algebra and you simplify, you get 100 factorial over L. 100 factorial, that looks like quite a large number, right? But, there's 100 factorial ways of ordering our numbers. So when we divide by 100 factorial, that's going to give us a 1 over L. And so on the upper right corner is the plot of the probability distribution of the length of the longest cycle. And so it's showing you what is the probability that the longest cycle has given, different lengths. And the highest probability is at 50 for a given one. And so now if we want to calculate what is the probability that we do not have a cycle of length 51 or greater, we take 1, which is the total probability, and then we subtract the probability we have a cycle of length 51 and the cycle of length 52, the probability we have a cycle of length 53, all the way up to the probability of a cycle of length 100. The biggest mistake people make in combinatorics or in probability is they double count an event. If I have a cycle of length 51 and I have another permutation that has a cycle length 52, could they be the same permutation? Your one has a cycle of whose longest length is exactly 51, and the other has a cycle whose longest length is 52. Could they be the same permutation? If I'm permuting 100 numbers. So one cycle, its longest length is 51. One, its longest length is 52. Could they be the same?
Do you mean they're that length, or they could be that length?
No, they're that length. I have one cycle that I'm thinking of, and the length of its longest,
Then no, they couldn't be.
no, because they have a different longest length. They have a property which distinguishes them. Imagine I'm trying to calculate what's the probability I get at least 2 kings in a 5-card hand of poker. Is everybody familiar with the deck of cards? I could calculate the probability I have the king of spades and the king of clubs. I could calculate the probability I have the king of hearts and the king of diamonds. I could calculate the probability I have the king of spades and the king of hearts, and I can go through all pairs of 2. Do I add them all together?
No.
No, because if I had all 4 kings, that would be counted in every set. If I had 3 of the kings, it would be counted in a lot of sets. There's a lot of double counting going on there. If I want to calculate the probability I have exactly 2 kings, that's very different than the probability I have at least 2 kings. If I have at least 2 kings, there's many ways to get it. If I just look at what's the probability I have the king of spades and king of hearts, that also includes the case where I could have the king of spades, king of hearts, and king of diamonds. So you have to be very careful with the counting. It is crucial in this problem that we are talking about you only open 50 boxes maximum, so that if you fail, there was a cycle of length 51, and you can't have 2 different cycles of that long length. If I had given you only opening 40 boxes, you'd be in trouble. Okay. So when you divide by the 100 factorial, because when I want to calculate the probability, there's 100 factorial ways to do this. The 100 factorial over L is how many ways can I do it with a cycle of length L, where L is at least 51. So if I want the probability, I divide by the number of possibilities. That's why I divide by the 100 factorial. And what I get is I get essentially a harmonic sum. I have 1 over 51 all the way up to 1 over 100. Well, for harmonic sum, where are you supposed to start summing? Do you start summing at 51?
Start at 1/2.
You start at, nope,
1.
at 1. So it's 1 plus a half. So what you do is you basically add and subtract the stuff that you're missing. So that's why we have minus H50. So we add H50 and then we subtract H50. And when we add H50, that's the sum of 1 plus 1/2 plus 1/3 all the way up to plus 1 over 50. When I add that, so then I had 1 minus 1 over 51 plus ... plus 1 over 100. I can write that as 1 minus 1 plus a half plus ... plus 1 over 100 minus 1 plus a half plus ... plus 1 over 50. I added and subtracted the same thing. I needed those, terms in the beginning. And so now what I have is I have 1 minus the 100th harmonic sum minus the 50th harmonic sum. And that's where the expression comes over there. And then they just estimate that as about 0.311 or about 31%. This is phenomenal. Originally, we had a probability of 1 over 10 to the 30th. This was you and I choosing the same air molecule in a room, that level of probability. The actual chance is about 30%. That's not bad. 30% is fighting odds. Now, you could ask what would happen in the limit. So if we had n and n over 2 would be 1 minus hn minus hn halves, or 1 plus hn halves minus hn. Does anybody remember approximately how big the harmonic series is? So this is going back to some calculus. So I thought it would be worthwhile to just spend a little bit of time reviewing some calculus, because this is some material you're supposed to know. And so let's just talk a little bit about how would you estimate something like this. And so let's hope this rings bells. The integral test. Does that seem familiar? So if you have a sequence that's either increasing or decreasing, you can estimate the sum with an integral. And so let's say, if the sequence an is non-decreasing or non-increasing, then the sum, let's do k equals 1 to n of ak, is basically the integral from 1 to n of f of x dx, where f of k equals ak, and f is nice. I'm not going to prove everything fully rigorously. I'm just going to, estimate and give you a sense of why this is true. Is this looking familiar? This is one of the most important results we have. It allows us to estimate sums very well. What's nice is the sum AK is going to diverge if it's the harmonic series. So if I'm missing a couple of terms in the beginning, it's not a big deal. So I'm going to just show why it's true for the harmonic series. So here's 1, 2, 3, ... n minus 1, n plus 1. I'm not going to worry right now about getting things exactly right. I might be off by a +1 or something like that. No one wants me to spend enough time to do it that rigorously. So let's see what's going on. At 1, we take on the value of 1. At 2, we take on the value of a half. At 3, we take on the value of a third, and so on. And then down here, it's getting really small. Okay? So we have a couple of ways to do things. So one way we could do it is I can make my boxes going to the right. Okay. Can you give me a function that equals, let's let ak equal 1 over k. Can somebody give me a function that equals 1 over k when x equals k and is a nice function?
1 over x.
1 over x. So almost always in problems like this, it's a search and replace. Take your sequence, wherever you see a K, put an X. And let's plot that. So if I plot this, are the blue block boxes going to be an overestimate or an underestimate? Overestimate. So we would get the integral from 1 to n of f of x dx is less than or equal to the sum, k goes from 1 to n of ak. Yes? And now let's get a upper bound. What I'm going to do now is I'm going to have all of my stuff go to the left. Is the integral greater than all the green boxes? The integral is above all of them except for the first box, right? So what I would get is this would be less than or equal to the first box, which is 1, plus the integral from 1 to n of f of x dx. So doing a crude analysis like this, I can actually estimate the integral to within 1. If I'm trying to estimate a probability, if I can get it to within 1, is that good?
No.
No, 1 represents 100%. Right? That's completely useless. I can do better, however. So with a little bit more work, I can do better. This is not a calculus class, so I'm not going to do the more work, but I just want to review the integral test. This is something that you should know. It's very useful for calculating stuff like this. And then if you want to read a little bit more, you put some links here, and you get what's called the harmonic numbers in terms of Bernoulli numbers. There's lots of wonderful relationships, but the key fact is that the nth harmonic number is equal to approximately the natural log of n plus the Euler-Mascheroni constant gamma, which is about 0.57, plus an error of size 1 over 2n. So if we use that, and if we use, hn is equal to the natural log of n plus the Euler constant gamma plus 1 over, was it 2n? 2n plus smaller. We had 1 minus hn, I guess it was plus hn halves minus hn. That was our probability. So that would be 1 plus the natural log of n halves plus gamma plus 1 over n plus smaller minus the natural log of n plus gamma plus 1 over 2n plus smaller. So when the dust settles, the gammas are going to cancel, right? Because 1 is with a plus, 1 is a minus. What's the natural log of n halves minus the natural log of n?
Natural log of 2.
Natural log of 2. So natural log of n halves minus the natural log of n is the natural log of n halves over n, right? So it's the natural log of 1/2, not 2. Right? The difference of the natural logs is the natural log of the quotient. And so this is just going to be negative natural log of 2. And natural log of 2 is about 0.7, maybe about 0.69. So this is about negative 0.69. So this becomes 1 minus the natural log of 2, it's terrible 2, plus 1 over 2n plus something smaller. So if n equals 100, we have 1 over 200. That's really small. That's less than a 1% change. Natural log of 2 is about minus 0.69, so this should be about 0.31. And that is what we were observing. So there's certain numbers that you just want to know in life, so you can do calculations quickly. The natural log of 2 occurs a lot. That's why I know it's about 0.69. But this gives you a sense of how we can quickly estimate, and we can see what's going to happen as n gets larger and larger and larger. The terms are going to go to 0, and it's going to converge to about 31% chance. So absolutely amazing that you can do this well. There's a lot of problems like this where the naive strategies make you feel like you are screwed, but you can actually do significantly better than you would expect. Okay. So now, this was just a nice application of group theory. And you can look up the 100-prisoner problem, and it will tell you some other places where this kind of knowledge helps us in terms of trying to find where something can happen, this chasing things down. It's a wonderful idea. So just reviewing from last time, we have groups acting on sets. So we have G as a group, X as a set. What is one set that you can always choose to have the group act on? The group itself. So that's always going to be a good choice. The question becomes, how do you want the group to act? You could act on it by left multiplication. It could act by right multiplication. It could act by conjugation. You could take an element X and you could go, if it's the group, you could go G inverse XG or GX inverse, either way. So when we define an action of G on X, we want two things to be true. We want the identity axiom and the associative axiom. So the identity axiom is that when you have E act on anything, you get back what you started with. And if we have G1, G2 acting on X, that's the same as first act by G2 and then act by G1. I don't think we've done anything all semester where associativity does not hold. Yep. There are situations where associativity fails. We don't like it. It's bad. You've got to be really careful with how you do things. Okay. We then had the very easy to be misread if somebody is writing with bad handwriting. We have G followed by a regular sized lowercase x. That's the orbit of x. That's take some element x and apply every element in G and see what you get. Then we have G subscript x. G subscript x is take all the elements in G that leave x alone. And that's called the stabilizer of x. If I give you an element x, is its stabilizer going to be empty, or does there have to be at least one element in the stabilizer? So is the stabilizer, could it be empty, or does there have to be at least one element in the stabilizer?
At least one element.
What's the one element that must be in the stabilizer?
The identity.
Identity. So not empty. Contains E. And in fact, the stabilizer is a group. I think we proved that last time. The proof is pretty straightforward. Just show that all the different properties hold. Okay. And so now we started with proposition 6.19. Let X be an X. The stabilizer is a subgroup. I think that's what we ended class with on today's Thursday, so it would have been Tuesday. And then the next is define a equivalence relation with the following rule. X is equivalent to Y if Y is equal to G of X for some G and G. So what that basically means is Y is in the orbit of X. Right? So the orbit of X is I can take any G I want and apply it to X. And what we're saying is Y is equivalent to X if it is in if it's in the same orbit. So we want to show that this is an equivalence relation. So equivalent relations have three properties: reflexive, symmetric, transitive. When you look at this, you might say, well, wait a minute, we're giving a preferential treatment to X. We're saying X is equivalent to Y if y is some g of x, is x going to be some other g of y? And we will see that almost momentarily in symmetric. So the first is reflexive. Is x equivalent to x? Can you give me some g such that x equals gx? Yeah, good. Yes. Taking g equals e gives x equals e times x. So the next is symmetric. If x is equivalent to y, is y equivalent to x? Well, x equivalent to y means there exists a g in g such that y equals g times x. We need to find something in the group such that x equals that times y. So must find g tilde in g with x equal g tilde y. What should we take for g tilde? G inverse. As g inverse y does equal x from above. So it's fine to just say x is equivalent to y. We just have to say y is some g of x. We get x as some other element of the group acting on y for free. And the last is transitive. If x is equivalent to y and y is equivalent to z, we have to show x is equivalent to z. Well, x equivalent to y means there exists, let's call it we'll call it g1 in g with y equals g1x. Y equivalent to z means there exists a g2 in g with z equals g2 of x. And note that g2 of y. And note z equals g2 of y, but y is g1 of x. And by associativity, that's just g2, g1 of x. So z is equivalent to x with g equal to g2, g1. And that completes the proof. So we do have a equivalence relation. Okay. Kind of makes sense, if x is in the orbit of y, y is in the orbit of x. If x is in the orbit of y and y is in the orbit of z, then x is in the orbit of z. This is saying if I can get from x to y, I can get from y to x. If I can get from x to y and I can get to y to z, is this always true? Can you always go in reverse? So if you've ever driven in cities with one-way streets, right, I may be able to drive down one street from one place to the next, but I may not be able to reverse the route. This happened when one of my friends who graduated a few years before me came back to visit and had forgotten that they had changed the streets to one way. And proceeded to drive the wrong way down the street. That, unfortunately, you can't do in general. So it's incredibly important that we have a group here acting on a set. So we do have the inverses. So when you were looking at what we were doing here, where we did the symmetric relation, we had to take G inverse. We had to have an inverse to show that the relationship was symmetric. Without that, it would fail. Now, the third part, which we did not really do last time, is there's a bijection between the set G, the group G mod Gx, and the orbit. And so what we do is we take as an input a coset of the subgroup G sub X, that's the stabilizer. We choose any element in the coset and we output G times X. So what's your first concern when you see this? I choose a coset. That's what G mod GX, that's what G mod the stabilizer is. It's going to be a set of cosets. So we choose some coset in here, and we choose any element in that coset, any element G. And we say that alpha on the coset is just G dot X. What's your fear? What do we have to be careful about with this definition? We should only be assigning one thing to a coset, right? So what's your fear? What could go wrong? So I have a coset C. I choose some element G that lives in C. And then from that, I'm going to get the element G times X. What could I have done instead of choosing G? Now I chose some element G. Instead of choosing that element, what could have happened? So E might not be in the coset. You're close. Instead of choosing G, what if I chose, I'm sorry,
See,
something else, right? What if I chose G tilde? And then that would give me G tilde times X. It said choose an element. It didn't say which element to choose. It just said choose an element. So what needs to be true? What has to be true? What do I need to be true about these?
Needs to be in the coset.
Well, G and G tilde both need to be in the coset. What must be true about GX and G tilde X? If I want this to be well defined, what has to be true? If I ask someone their age, should I be getting multiple answers? No.
So they have to be equivalent.
More than equivalent.
They need to be the same.
They need to be the same. These must be the same. If they're not the same, then the map is not well defined. What we're basically saying is the map only depends on which coset you're in. We've seen examples of this before with clock arithmetic. If I want to multiply two numbers and then reduce, that's fine. It doesn't matter which representatives I take. I'm going to get the same answer on the clock. And so here, when we're defining this map, as soon as you see choose an element, you have to show no matter what element you choose that it's well defined. So the first is the map is well defined. So if G and G tilde are in the same coset, then there exists a C in GX such that G equals G tilde times C. So if they're in the same coset, they have to differ by some element in the stabilizer in G sub X. So G acting on X is the same as G tilde C acting on X. But by associativity, that's the same as G tilde CX. But C is in the stabilizer of X. So since C is in the stabilizer of X, what is CX? It's just X. So it is well defined. So we are okay. So if you have two elements in the same coset, then they have to differ by, multiplication on the right by some element in the coset. And since our coset is just all elements that stabilize X, that leave X alone, then if I want to figure out what is G acting on X, that's the same thing as G tilde C acting on X. So G and G tilde don't have to be the same element, but they differ by some multiple on the right that's in the stabilizer. And when that hits X, it doesn't matter. If it hits something other than X, it could matter. We're not saying that G and G tilde have the same action on every element. We're just saying when you look at what they do to X, they give you the same thing. Okay. So now we want to prove that if G is finite, then the cardinality of Gx is equal to the cardinality of G divided by the cardinality of Gx. So we want to prove the cardinality of Gx equals the cardinality of G divided by the cardinality of G sub x. So there are three things here. What is this first quantity? What is Gx?
On the order of.
What is Gx? What object is Gx?
No, I have a question.
Yes.
Can you go back to the other thing?
Sure.
So in this, the coset is part of the stabilizer, like C is the stabilizer? Or
C is in the
this-
stabilizer.
And then you're applying the stabilizer to the set,
To X.
to X.
So what we're saying is we want to define a mapping from the cosets, from the elements of G mod Gx. These are our cosets. And so the cosets G mod the stabilizer, we would have the identity Gx, then maybe G1 Gx, maybe G2 Gx, dot, dot, dot. Those would be the different cosets.
The cosets are always something in a stabilizer?
The cosets are some multiple of the stabilizer of X. So just like when we looked at the integers mod 12, we might take our subgroup to be the, me out a blank page. When we did, Z mod 12Z, here the group G maybe was the integers, and our subgroup was 12Z. And in the cosets, Z mod H, or I guess Z mod 12Z were 0 plus 12Z, 1 plus 12Z, all the way up to 11 plus 12Z. Those were our cosets. And here we're writing things additively. In what we were doing over here, we're writing things multiplicatively. So instead of writing 0 plus our subgroup, we're now writing E times the subgroup. Instead of writing 1 plus the subgroup, we're now writing G1 times the subgroup. And so we have our fixed subgroup H, which in this case is the stabilizer of X. So our subgroup is Gx. So for us, Subgroup H is the stabilizer. And now we're looking at the cosets. And so G mod GX is the cosets of G by H. And H is going to be just the stabilizer of X. And so I will, if G is finite, I'm only going to have finitely many cosets. But when I give you 1 plus 12z, what's an element in 1 plus 12z? 1. What else? What else?
25.
25, or it could go negative 12. All of those would be elements. So if I take a representative, if I take something in 1 plus 12z, I have a lot of choices of things I could take. I could also write 1 plus 12z. I could write this as 13 plus 12z, and that would be the same as 1 plus 12z. So if I change what element I use to write it, it's still going to be the same set. And so what we're saying over here is if I choose an element of a coset, I can have that element act on X. But what if I chose a different element of the coset? What this is saying is the action of a coset doesn't matter which element you choose to figure it out. You can use whichever one you want. If you think back to calculus, if you know the limit exists, you can choose any path you want to compute the limit. In multivariable calculus, you'll often come straight at the origin along a line. So if you know the limit exists, you might try to calculate it that way. If the limit doesn't exist, then you're in trouble, and you have to show no matter what path you take, you get something that's well defined. What we're saying here is I'm going to define a map, and no matter what element I choose in the coset, it's going to have the same effect when I apply it to X. So if I take two different things that are in the same coset, they have the same impact. This is in some sense where we're getting this notion from earlier in the proposition of we want an equivalence relation. Two elements are equivalent if they have the same properties for things we care about. If I have two pennies that both have a 60% chance of landing on heads and a 40% chance of landing on tails, but one is blue and one is red, does the color matter? No, if I'm simulating probabilities, the two coins are equivalent. The fact that they're not identical doesn't matter. The fact that they give the same probability for heads and tails, that's all that matters. So what this is saying over here is that when you want to try to understand a complicated structure group, the idea is break it up into something smaller and understand that. And then try to write your group as something involving that small thing and understand how things are combined. So maybe we can understand the stabilizer, maybe we can understand the set of cosets by the stabilizer and piece those together to understand G. So the goal is to try to understand G by breaking it into easier, digestible pieces. The stabilizer of X is a really nice thing to look at. It's all things that leave X alone, yeah.
So in that example, would you say like the multiple of 12 are the stabilizer for that? For the example you showed for the block multiplication of 12.
Right. So I mean, we haven't really talked about what element we're looking at to stabilize, right? So here I'm trying to find a map that stabilizes. I'm trying to find all the elements that stabilize a given element. Question? If somebody has a question, almost surely somebody else has that question as well.
I don't know what my question is yet.
So what we're just trying to say here is, if I have the set of cosets, a coset is a set of elements. I want to define a function on the set of elements. I don't want to have to define the function for every one of the infinitely many elements of 1 plus 12z. If I can figure out what it does for one element, if I can figure out what it does for 13, that would be the same for 25, that'd be the same for -12. I'm looking for a map where I only care about figuring out what it does for one element of that coset. Everything will be the same. The whole coset acts the same.
So the coset is,
The coset is the input. So when we have this map, the input of the coset, the input is the coset. So here, this is the input. The input is the cosets. And the output is the orbit. So you take a coset and its output is, something in the orbit of X. It makes sense that it's got to go to something in the orbit of X, because we have G acting on X. And so the orbit of X is just where it goes. And what it's saying is, if you give me a coset, I can tell you how I want to define this. And that's my map alpha. And I'm going to define what it does to a coset by just saying, hey, choose anything in that coset, choose any G in that coset. And I'm going to define my function on the coset to just be G acting on X, where G was a randomly chosen element in the coset. And your first concern is, well, what if I chose a different element in the coset? The coset could have many elements. I'm defining a map on the whole coset. It's like anything you take in the coset is going to give you the same value. So instead of defining my map on each element of G, I'm defining it on a much more blurry scale. I'm saying if two elements live in the same coset, I can't tell the difference.
and like a coset would be given to you, or you have to determine?
Well, you get the coset by the stabilizer. So this is what we did earlier in the semester when we looked at G mod H. And your two cosets are either disjoint or the same. So if I have, a group G and I have a coset H, then what I can do is I can look at G mod H, and maybe that's going to be E plus H, A2 plus H, AN plus H. And every element in G is going to be in one and only one of these cosets. So the union K goes from 1 to N of AKH is going to be the group G. And the reason is what I can do is, let's say I could look at the cosets, G1 plus H, G2 plus H, G size of G plus H. That's all the cosets. And because H contains the zero element, this is clearly, the union is clearly going to be everything. But two cosets are either the same or entirely disjoint. So I can then take this whole list of cosets and then just keep the distinct ones. So two cosets are identical or disjoint. So take a set of disjoint cosets such that have everything. And that's where we get our the union K goes from 1 to N of AKH. So if I give you a group, I can easily form the set of cosets, by some subgroup H. And if I look at all the cosets, well, I clearly get all of G because I just range over all elements of G. G1 plus H, G2 plus H, all the way up to G cardinality of GH. So you give me any G, well, it's clearly going to be in the coset G plus H. You give me a G prime, it's in the coset G prime plus H. Every element in G is contained in one of these cosets. And then when I have this list, some of these cosets may be the same, some of them may be different. And we proved that two cosets are either 100% the same or 100% different. They either have no elements in common or they're the same. And so if I have this list, I might as well prune it. And I start off with the first one, G1H. Then I look at the second one, G2 plus H. Is that the same as G1H? If yes, I don't need it. If it's different, then I'll keep it. Then I look at G3 plus H. Is that the same as one of the things I already have? If yes, prune it. If not, keep it. And I just keep marching down. What's the simplest coset you could, what's the simplest subgroup H you could take?
G,
G, and the other simplest one,
GI.
E, right? So if H equals E, then N is just going to be the size of G. And every element is going to be its own coset. If H equals G, then how many cosets do we have? If H is all of G, how many cosets do we have? Just one. And then it becomes more interesting if you choose something that's larger than the identity, but smaller than all of G. And then you'll have some number of cosets. And for certain things, it's enough to just know that two numbers are equivalent. You know, if you've looked at sines and cosines, if I want to evaluate sine and cosine, do I need to know exactly what argument I'm evaluating at? Only up to a multiple of 2 pi, up to an integer multiple of 2 pi. And so for those functions, if I'm trying to define sine, I don't have to define sine in some sense on the entire real line. If I just define it from minus pi to pi, I can extend it periodically. What we're just saying over here is I have a map from the set of cosets of G where the subgroup is the stabilizer of X. That's a good subgroup to look at. And it's going to give me a collection of sets. You know, we're not used to defining functions on sets. You know, we're used to, you give me a number, and I'll give you the value of the function on that number. Well, these are very special sets. The elements are related to each other. They're all in some sense, equivalent. They differ by multiplication on the right by something in the stabilizer. So when they act on X, they give the same output. And that's why we can define the map like this. It doesn't matter which element we choose, we're going to get the same output because they differ by multiplication on the right by something in the stabilizer. And that's why we have at the very end, we have this chain starting with, well, G acting on X. Because G and G tilde are in the same coset, I can write G as G tilde times something in the stabilizer. And then we use associativity, and then by using associativity, this is the same as have C act on X and then act on it by G tilde. And because it's in the stabilizer, C acting on X just gives you back X. And so we see that if you have two elements that differ on the right by something in the stabilizer, then they give you the same output when they act on X. Does this clarify enough? So the next part is we want to prove that the cardinality of Gx is the same as the cardinality of G divided by the cardinality of G sub X. What is Gx?
The orbit.
The orbit. So this is the orbit. G, that's the group. And what's G sub X? The stabilizer. Okay, so we want to show something like this. So let's recall Lagrange's theorem. So we had a group G, we had a subgroup H, and then the index GH was equal to the number of cosets of G by H. Then the size of G was the number of cosets times the size of H. And the proof was that we could write G as the union, K goes from 1 to the number of cosets of, I'll just write it as, AKH. And all of these are the same size. So we could write G as a union of cosets. Each coset had the same size. How many cosets do we have? G colon H. It's the definition of what G colon H is. It's the number of cosets. So because the cosets are distinct, and because their union is all of G, we've just counted the number of elements in G two different ways. One, on the left, it's just G, and on the right, it's this union of cosets. Okay. So this is Lagrange's theorem. Does this look similar to what we have? So if you look at what we're trying to prove, we want the number of elements in the orbit is the size of G divided by the size of the stabilizer. How could you rewrite that? How could you rewrite it so it looks more like Lagrange? Yeah, multiply by the stabilizer. Almost. Multiply by not the stabilizer, by the size of the stabilizer. So we would get the size of the orbit times the size of the stabilizer is equal to, and actually, let me put it on the left-hand side so it matches more closely. So we get the size of G is the size of the orbit times the size of the stabilizer. We're done if the size of the orbit equals the index of G and GX. And then we can just win by Lagrange. So this is why we spent some time at the start of the semester proving great results about groups. We can now get some dividends from this. So we're using Lagrange's theorem here. And we quickly reviewed it. And we saw that what we're trying to prove in this proposition is essentially just Lagrange's theorem, if we properly interpret. So one of the challenges here is figuring out what should we choose for our different objects? What should I choose for my H so I can use Lagrange's theorem? Well, I want H to be my stabilizer. And so the only thing we're left with showing is that the cardinality of the orbit is equal to the number of cosets. So if you look at what's going on here, we have a map. We have a map from the cosets to the orbit. If we can just show that two different cosets go to different elements in the orbit, and everything in the orbit is hit, then we'd be done. If basically we have an isomorphism, if we have, you give me something, you give me some coset that goes to one element in the orbit, and I can't have another coset going to the same thing, then we would be done. And so we're assuming right now that our sets are finite. So we need to show that the cardinality of G by the stabilizer is equal to the size of the orbit. Okay. So the first thing is, do you think everything in the orbit is hit? If I give you something in the orbit, do you think that something is going to hit it? So we have to show, so if we show the map is 1-to-1 and onto, we win. Well, the orbit is all the action of G on X. So you give me anything in the orbit, I can find something that hits it. So onto isn't bad. Let's say Y is in the orbit. So there exists a G such that Gx equals Y. Right? But G is equal to the union of the orbits. I mean, the union of the cosets. Let's call it maybe, AK GX. Right? It's got to be equal to the union of all the cosets. So G in G implies G is in some coset. And then that coset will get mapped to that element Y. So that coset maps to Y. So we're just using the fact that if you look at the union of all the cosets, you get all of G. So if I have some Y that's in the orbit, how am I in the orbit? Well, there had to be some G that acts on my X and gives me Y. That's what it means for Y to be in the orbit of X. I can somehow get to Y by acting on it with some element G. And then that means it's got to be in some coset. Okay. So now we have the onto. Now we have to do the 1-to-1. So say G1, G2 in different cosets. And we know that it doesn't matter which element I choose in a coset to figure out what the map does. So could G1x equal G2x? If yes, then it's not going to be 1-to-1. So assume happens. Assume G1x equals G2x. Then what must be true? We want to prove that. And they don't have to actually be equal to each other. We're assuming that G1 and G2 are in different cosets. I'm assuming that my function is not 1-to-1, so I'm going to try to get a contradiction. This is a proof by contradiction. What do you think I'm going to try to contradict? They're in different cosets. So I want to show G1 and G2 are in the same coset. If G1x equals G2x, what can I do to both sides?
Multiplied by the inverse of X?
Nope. You can't multiply by the inverse of X because X is a set.
Oh.
Right? They'll be saying, I want to multiply by the inverse of a vector. I can't do that.
Yeah.
So instead of multiplying by the inverse of X, what can you multiply by the inverse of? You have two right answers.
G1 and G2.
Yeah. Which do you want to do? G1 or G2?
G1.
G1. So then this is the same as X equals G1 inverse G2X, which by associativity is G1 inverse G2 of X. So what do you know about G1 inverse G2?
Stabilizer.
It's in the stabilizer. So thus, G1 inverse G2 is in the stabilizer of X, which means G inverse G2 equals G1 inverse G2 equals G for some G in the stabilizer, or G2 equals G1G, so in the same coset. So if we just unwind what happened, once we know G1 inverse G2 is in the stabilizer, then we know it has to equal some element in the stabilizer. Let's call that G. And then that means G2 is going to be G1G. So they're in the same coset. I can write them as just they differ by multiplication on the right by something in the stabilizer. So we have shown that we have a nice one-to-one onto map. If you have two finite sets and you have a one-to-one onto map, do they have to have the same number of elements? Yes. If the sets are infinite, that is not necessarily true. As long as the sets are finite. If you have a one-to-one onto map, they have to be the same. Okay. How many of you have seen the 3x plus 1 problem? There's a lot of great quotes about this. My two favorites, this was a Soviet conspiracy to slow down American mathematics. And mathematics is not yet ready for a problem like this. So if you're planning on being a teacher and you need to come up with a sequence for students to look at, this is one of the simplest ones to define. So we do the following. an plus 1 is equal to 3an plus 1 if an is odd, or an divided by 2 if an is even. So someone give me a nice positive number.
8.
8, good. So you do not know the problem well enough to give me the painful number. Do you know the painful number? Don't say it out loud, but do you know the painful number?
No.
Okay.
I know the non-painful numbers.
All right, so 8 is even. So 8 goes to 4, 4 goes to 2, 2 goes to 1. And now what does 1 go to? 4. And it cycles. Somebody give me another positive number.
32.
32. All right, 32 is not too bad. 32 is even, so it goes to 16, goes to 8, and cycles. All right, somebody give me an even number that is, somebody give me a positive number that's not a power of 2.
7.
7. All right, so 7 is odd, goes to 22, goes to 11, goes to 34, goes to 17, goes to 52, goes to 26, goes to 13, goes to 40, goes to 20, goes to 10, goes to 5, and what does 5 go to? 16. What would you conjecture based on this?
Everything should go to 1.
Everything should go to 1. I will give you an A+ for your entire remaining undergraduate career if you solve this one. This one is way beyond open. Yep. It's been connected to so many difficult problems. What I love is this is something that you can state to an elementary school kid, and they will be able to understand what you're talking about. You can ask them, can you at least find infinitely many numbers that go to? Then you could also do the accelerated map. So it's on odd numbers. an plus 1 is 3an plus 1 over 2 to the k, where 2 to the k divides 3an plus, but 2 to the k plus 1 does not divide 3an plus 1. So what it's basically saying is just remove all the powers of 2 you can in one step. So 32 would immediately go down to 1. 16 would immediately go down to 1. When you had 7, you wouldn't go 7, 22, 11. You would just have in the accelerated map, 7 go straight to 11. And so what you could then ask is, are there infinitely many numbers that go to 1 in one step? Sure, powers of 2. Are there infinitely many numbers that go to 1 in 2 steps? We can't even prove a positive percent of numbers go to 1. This problem is very open. We can prove like x to a power less than 1 go to 1, but we can't prove a positive percent go to 1. So here you're stolen from the web, and if you look very carefully at the bottom left, you can see where it was taken from. So I'm not actually stealing, so I can keep my job. This is a tree of what happens. And so you can see the different branches. And I wanted to do this because this illustrates a little bit of a difference between this map and what we were doing, and emphasizes why we want to have a group acting on a set. So if you look at the number 3, here is the path from 3 all the way down to 1. And then I could take let's do 341. Actually, let's do it in a different color. And 341 also comes down to 1. So I have 2 different numbers that go all the way down to 1. So if you look at the orbit of 3, and if you look at the orbit of 341, they both land on 1, and then they cycle 421, 421, 421 for all eternity. But I can't get from 3 to 341. I can't get from 341 to 3. This is very different than what we had before with a group acting on a set. Because we had the group acting on a set, if I could flow from x to y, I can flow from y to x. And so 2 orbits were either the same or entirely disjoint. Here, the orbit of 3 and the orbit of 341 share some elements, and then there's other elements that they don't share. If you want to be an ass, have somebody do the number 27. Okay. That takes an incredibly long time to iterate down to 1. There's a tremendous amount that's known about this problem in terms of how long it's going to take for numbers on average. And so if I give you a number of size, say 10 to the n, I know roughly how long it should take before it iterates down. I do not want to start the orbit stabilizer theorem with just 5 minutes left. That is a recipe for disaster. But this is just going to be a good place to end, and I'll just do a very high level. This gives us a formula to count how many elements there are in X based on how many elements there are in G and how many elements there are in the different orbits, in the stabilizers of the different orbits. Why is this going to be useful? We're going to be able to use it to show that the center has some nice properties, that if P is prime and G is a group of size P to the n, the center is not empty. We'll be able to show later that if we have a group of size P squared, the group is abelian. Later, we will do the CeeLo theorems, and we will be able to show that if you have a group G and P to the n is the highest power of P that divides, then there must be a subgroup of that size. And in fact, we even have some understanding of how many subgroups of that size must there be. And this is going to really help us understand the structure of these groups. All right, so this is a good place to stop. So we will stop.